Example number 1. Identify the lines of symmetry in each tessellation. Now, it would be a real sad day in my life if I did not take a few moments to just unpack what a tessellation is. So according to good old Google, a tessellation is the process or art of tessellating a surface or the state of being tessellated. What the heck does that mean, actually? An arrangement of shapes closely fitted together, especially of polygons, so many-sided, straight-sided shapes, in a repeated pattern without gaps or overlapping. So somebody who was actually super impressive with tessellations was an artist named Escher, M.C. Escher. He was famous for a lot of things, so I've just kind of highlighted one of them. This right here is an optical illusion because it looks like the water is flowing, 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 and then falling down. Wait a second, flowing out. So the water would literally have to be flowing up. What? That doesn't actually happen in real life, but this is a perpetual motion machine with Penrose triangles, and it was created in 1961. Now, for me, Escher is kind of like a sinkhole of Google searches, because what I could do right now is Google what Penrose triangles are, or you could do that. The Penrose triangles are actually these little shapes that are right here, and it kind of what makes it into an optical illusion is the way that he plays with. See how this is going behind? Okay, then all of a sudden it is on top of them. And so he's playing with a different shading to make an image that looks all right in our brains. Our brain can make sense of it, but when we really pay attention to all the different shadows and that sort of thing, it gets really confusing really fast. Like how can water flow upwards and then down onto a waterfall when it doesn't really feel like it's going down at all? But that's a total digression. What M.C. Escher is also excellent at is these ideas of tessellation. So it's this idea of shapes that fit together to create a broader work. Now this right here is a little bit of a looser tessellation, but there are some other ones that are just fabulous. So if we're looking specifically at his tessellations, we would look here, and we would see this blackbird here, and we see this repeated pattern of the white bird as well, and they fit together absolutely perfectly. Another one that I love so much is this little lizardy guy one. All the little lizards, they all fit together. So even though it doesn't fit the usual definition of a polygon, okay, because there are curved edges to these little guys, it does it does fit the bill in that they are repeated patterns that have no gaps, that fit together perfectly. Yeah, so there's my digression. Love M.C. Escher. You can you can Google much more and find out much more about him on your own. I just love it when math and art coincide. M.C. Escher is a really great artist that can marry both of those worlds really well together. All right, so back to Mathland. Example 1. Identify the lines of symmetry in each tessellation. And we know that they're tessellations because they fit together and they're repeating. Same with this one, they fit together and they're repeating. Before we move on, we have to mention I have to mention one thing here. This is an isometric grid. So you're noticing that, so this one is below is the next dot, and then below is the next dot, and then below is the next dot. It's on a straight line grid. This one, the grid is kind of more like, the grid is on a diagonal. This one right here is isometric grid. So I only see one, and it's straight down the middle right here. That is our line of symmetry. If I were to say this right here is my line of symmetry, it's not exactly right, because this and this point, yeah, they're equidistant, but when we move a little bit further here, this one is closer to the line of symmetry than this one would be. So we don't have a horizontal. Let's experiment if we have a vertical. Oh, sorry, an oblique. So this point and this point feel equidistant, but we have this line here that does not look like this in the reflection line. So we do not have an oblique line of symmetry. It truly is just vertical. Now when we get to squares, even though they're kind of boring shapes, they have pretty fun symmetries. So we have just the straight up perpendicular symmetries like this, vertical and horizontal straight lines. But then we also have those oblique symmetries. So we have this symmetry right here, line of symmetry, and this line of symmetry, just like that. All right, let's move on to example 2. Identify the triangles that are related to the shaded triangle. So this, it will show up in red on the video, but maybe gray in your notes, by a line reflection. Now we don't want rotational, we don't want anything twisted or anything like that, but we just want straight reflections. So if I were to draw a line right here, this one is kind of the most obvious to me. If we would draw a line at y equals 3, we would have reflection image B, because all the points on these two triangles are an equidistant away from each other. Now I have this one right here. This is another kind of easier one for me to see. When I would say x equals 5, and that produces the reflection image of A. Now there's one more. Now this right here experiences a translation in that every single point is just moved up 1, 2, 3. So moved up 3. However, it's not a reflection, because if I were to draw a line right in between them, each point would not be equidistant to the line of symmetry in dispute. There is one more though, and I want you to think about our oblique lines, even though it's a little bit more difficult. This and this, that's a reflection. So to find the line in between it, I'm going to just draw a few dots, just so I have a good kind of guide to draw my line. And there it is. Now, it asks us to describe the position of each line of symmetry. In grade 9, we don't have the tools to describe what the equation of the line is. If it's oblique, we can, if it's horizontal or if it's vertical, we got those tools. But what we can say is the line that goes through the points. Let's just pick 2 points. Why not? So 1, 2, 3, 3, 7, and 7, 3. Just to be confusing, why not? So the line that goes through the points 3, 7 and 7, 3. I can be more specific. I can say the straight line that goes through those points, and it produces reflection image D.